Voltage and the measurement of the work function. We start with a comment on energy and work. Work is a quantity of energy that we can use however we wish, and it's associated to potential energy or electrical energy. These are energies that we can use. And we recall Carnot principle. So if we have a quantity of energy and we want to convert it to work, then a part of it will be work that we can extract, but not all the energy can be converted to work. We need to give a part of energy to another focus in order to extract the entropy coming with the initial energy, so that the efficiency of the conversion will be the work obtained with respect to the initial energy that we had. So this is the Carnot principle. In a chemical system, the work that we can obtain from the system is given by the difference of free energies. And the electrochemical potential is the free energy per particle in a system of electrons. Therefore, the work that we can produce from a chemical system is related to the difference of Fermi levels. So, for example, if we have a semiconductor, then this is the valence band and conduction band, and we can make an excitation of an electron-hole pair. But then this will come to relaxation at the band edges, so that the energy available is the gap energy. This is the energy of the electron-hole, separated electron-hole pair. But then we have a difference of electrochemical potentials, and this is the voltage that we can obtain, and the rest has to be given as at the cessation of entropy, so that there's a difference of the energy of the carriers and the energy, the potential energy that we can extract from the system. In a device, we have contacts. They are called current collectors, and they are normally metals, but the electrode can be extended with other nanostructured films. There are many options, but the metals are important because they are the parts where we can fix the final Fermi levels, and they are metals, so they don't have an internal structure. So here we will fix the Fermi levels, and inside there can happen a lot of things. So what is a voltage measured by a voltmeter? The voltage is the difference of electrochemical potentials of electrons in the metals, in the current collectors. So here we have a stable Fermi level, and here we have another stable Fermi level. This is coming from electrons, or from holes probably, but we have stable Fermi levels in the current collectors, and the difference is the energy related to the voltage. There is a Q, the elementary charge, to convert voltage to energy, and there is a minus sign because these diagrams are always the electron energy, so we multiply it by a minus. So when we apply a negative voltage to the left contacts, this is going up, the Fermi level at the contact. When we apply a positive contact, this is going down. But the voltage then is related to the difference of the Fermi levels. In a device where we inject current applying an external voltage, we will induce an electron flux inside the device. In a device that produces a potential, like a battery, then we have a flux of electrons going from the negative to the positive terminal, so that the electron current will be going out in this way. There is a standard denomination of the contact, so the cathode is where electrons go inside the device, and the anode is the positively biased electrode. So that this is for a cell such as an electrolyzer. When we inject current from outside, we have the cathode entering electrons and the anode. So the electrical current is going out at the cathode. A solar cell is like a battery. We are not injecting the current, rather it will be producing the current. So the cathode is where the electrons leave the device. This is the cathode, and it is the negative electrode, which is higher than the other one, which is the anode. So that current flows into the device. This is the electrical current going to the device under illumination. We now see the contact potential difference. And the experiment we are going to consider is to put in contact two different metals. They are different because you can see that they have very different work functions. At the right is much larger, so that the Fermi level is deeper with respect to vacuum level. And when we bring them into contact with a wire, or because they are very close to each other, can exchange electrons, then there will be a flow of electrons from one to the other. And the flow of electrons is going from the high Fermi level to the low Fermi level. Electrons go this way, they go downward in the energy diagram. So electrons will pass to the right and will leave negative charge at the left. So they build an electrical field and they build a variation of the electrical potential. When they are in equilibrium, then we have a step of the vacuum level, and this is called the contact potential difference, and also the built-in voltage. So now, about the voltage, we said it's a difference of the Fermi levels of the contacts. So this connection has two contacts, but if we connect the two metals, they will come to equilibrium and establish this situation with a contact potential difference. But of course, there will be no difference of the Fermi level. So the voltage, of course, is zero. So there is no way that we can measure with a voltmeter the internal contact potential difference or built-in voltage, because this connection of metals is not giving a voltage, it's not giving an energy by itself. To have a voltage, we need to have a difference of the Fermi levels, and here there is no voltage. When we take this capacitor structure of the metals with different work functions and apply a voltage, what is going to happen is that initially we have this contact potential difference. This is the vacuum level. And if we apply voltage here, then we're going to raise the vacuum level and change this contact potential difference. So this is when they apply voltage. So the difference of the vacuum levels is modified by the applied voltage, because now the Fermi levels are not in equilibrium. They differ by the applied voltage. Now, this situation can be continued until we flatten the vacuum level, and then we return to this situation. But in this case, because we have applied the voltage, and this voltage will be the built-in voltage. If we apply a voltage to a semiconductor, the situation is a little bit more complicated because the Fermi levels can vary inside a semiconductor, but nevertheless, if we start with a p-type semiconductor in equilibrium, so there is a single Fermi level, but then we can rise the Fermi level of electrons, for example, and then the Fermi level will go inside, and different things can happen by transport, recombination, etc. But nevertheless, the voltage is related to the difference of the Fermi levels at the contacts. And when we increase more the Fermi level, then there will be other changes inside, but still the voltage is related to the difference of Fermi levels. So when we create a difference of Fermi level, and this is the central idea of energy devices, we now create a difference of Fermi levels in the device, and then we are obtaining a voltage because these 2 points are different, so that we are obtaining a voltage. It can be a battery, or it can be by photogeneration, a solar cell, etc. But then this is the way that a device produces energy, because we have achieved a separation of the Fermi levels, different at the two sides. We now go to how to measure the contact potential difference at the junction between two materials. And then we go to the situation in which we have a metal that we are testing. We want to know the work function of this metal, and we come close to it with a probe of a metal that has known work function. They are going to build a built-in voltage or contact potential difference, and this contact potential difference equals the difference of the work functions, and we need to measure it. So if we measure this difference and we know the reference work function, we will learn or measure the work function of the test material. This measurement cannot be done with a voltmeter. This we explained before already, but we can get another method, which is the Kelvin probe. What we're going to do is to bias the reference, the probe, and by oscillation, we can detect the charge because we will obtain capacitive current. And this capacitive current disappears only when there is no charge at the surface. And this is exactly the situation where we have flattened the contact potential difference. There is no potential difference. So at this point, we know that we are measuring here the built-in voltage. So this is the way to learn this built-in voltage, and from here we can construct the internal work function. The Kelvin probe method can be used to test the surface vacuum level of any material. We have a material here, and at the surface it will have this vacuum level. So we can come with a probe and measure this difference. This is the reference vacuum level, and we can measure this difference, and this is the contact potential difference. So we can make changes in the material and observe how is the vacuum level going up and down. Here we have one example of a p-type semiconductor, and we are coming with a probe, and if they have the same work function, the vacuum, the contact potential difference will be 0. But if somehow we construct a charge separation at the surface, there will be some band bending, and then there will be a displacement of the vacuum level, and then this can be measured by the Kelvin probe method. So we can monitor the changes in the semiconductor by this method. For example, we can apply illumination and then obtain a change of the band bending, and then this will be detected in the surface change of the vacuum level, and this is called the surface photovoltage. So here we can see several examples of applying the Kelvin probe to a given semiconductor with a surface oxide layer. So here is the initial contact potential difference, which is the difference of vacuum level between the sample and the probe. And when we change the medium, this is going to change, so that we can see that we are going to modify the contact potential difference in different cases, so we know which is the state of the surface. Then by applying illumination, we can track the surface photovoltage in different situations. The Kelvin probe force microscopy consists on scanning a probe through a sample, and then, since we are measuring the contact potential difference at each point, then we are getting a picture of the electrical potential distribution along the sample. In this case, this transistor is biased, and we can say that it's more or less homogeneously distributed. The potential is linearly distributed across the graphene sheet. This is the same experiment on a perovskite, on two different perovskite solar cells. The cell has been cut, and we see the different internal structure with the contacts and the active zone. And then we can track the potential by scanning the probe across the length and observe the internal distribution of electrical potential in different conditions of bias, light, etc. And we get a lot of insight about how the device is working inside.